Hello everyone, and today we're talking about a special topic using integration, and it's the volume of solids using circles. So let's get started on that. So we're going to learn how to calculate the volume of a solid created by rotating an area, so that would be a 2D space, an area around an axis. In today's examples, we're always rotating around the x-axis. So we'll start with a basic function, a linear function, f of x equals 2x, and we'll limit the domain to be between x of 0 to 3. So you'll see it on the red line there. When we integrate this function, we'll get the area as shown, which is basically a triangle. We'll rotate this triangle 360 degrees, so completely around the x-axis. And that will give us a shape something like this, which would be a cone if we could see the 3D shape on our computer screen. The cone will have a base of a circle with a radius of 6. So, symbolized by the blue cone there. Now we can double check our calculus work by first using the formula for volume of a cone, which is a well-known formula. The volume of a cone is 1/3 times the area of the base times the height of the cone. In this case, the height of the cone is 3. So the area of the base comes from the formula for area of a circle, because it's a circular base, of pi r squared. So this gives us an area of the base of 36 pi if we leave it in terms of pi. Okay, so plugging that area, that base in, we get 1/3 times 36 pi times 3. Well, the height of 3 and the 1/3 will cancel each other, leaving us just with a volume of 36 pi, which is approximately 113.1. Whatever your units would be, I guess cubic centimeters or cubic meters or something like that. Now, let's see the same thing using integration. Keeping in mind the volume, the area of a circle is pi r squared. So with integration, basically we're dividing the cone of height 3 and radius 6 into circles. For small circles on the left of radius of 0, or basically non-existent, all the way up to larger circles of radius 6 on the right, and all the various radiuses in between for the height of 3. So basically you'll see here in the integration, the formula for the circle is embedded there. We're integrating from 0 to 3. We have our pi times the formula for the cone of 2x that draws us our line, and 2x squared because the radius is squared. So first we'll move the constant of pi out front. We don't need that cluttering our way in the integration. And then we'll resolve the power of 2 by distributing that inside, giving us 4x squared. Okay. And then we'll wind up with something like this. So we're evaluating from 0 to 3, pi times the result of the integration of 4x squared, which is 4x cubed over 3. And so that basically gives us pi times 4 times 9. The 9 from 3 power 3 of 27 divided by 3 is 9. So it's pi times 4 times 9, or 36 pi. So you see it matches exactly the formula for the volume of the cone, which we saw in the last part. Now in example 2, we're going to see a more complicated function, one that we cannot use a known formula for to find the volume. So we'll start with our function, which is 1 over the square root of 2x plus 2, as shown on the green line there. We're going to limit our x values to be 1 to 6 and create an area underneath that. We'll rotate this area 360 degrees around the x-axis and get something approximating this. Now there's no known formula for this shape, so we're going to go right to the integration step. So first I'll point out that for simplification, 1 over the square root of 2x plus 2 is the same as, in brackets, 2x plus 2 to the power of negative 1/2. A power of 1/2 is the same as a square root, and negative because we're holding it in the denominator and now showing it in the numerator, so we have to flip the sign of the exponent. Same as we saw before with integration, this is based upon the idea of area of a circle, so I have area is pi r squared up there on the right in red. Well, let's go. So I show the integration from 1 to 6, pi times our function, 2x plus 2 to the power of negative 1/2 squared dx. We'll move our pi out front so it's not cluttering and bothering us. And we'll also simplify the exponent with the 2 outside and the negative 1/2 exponent inside. We'll multiply together to just give us a regular old negative 1. We'll have to use u substitution now. So u will become 2x plus 2. So the derivative of u will just be 2 dx. And that gives us pi over 2, integrating from 1 to the 6, 1 over u du. So we get pi over 2 because we can see that du is 2 dx. We don't have a 2 in our answer, so we'll have to multiply by 1/2 out front, and 1/2 times pi just becomes pi over 2. And inside the integration we still just have 1 over u du. So we'll still keep going. And so 1 over u will become the log, the natural log. So then we get pi over 2 times the log, replacing the u back, undoing the u substitution, of 2x plus 2. Now we need to evaluate that. So we have pi over 2. Evaluating from 1 to 6 means that we're plugging in 6 and then 1 into 2x plus 2 into the natural log, which gives us the log of 14 minus the log of 4. Subtracting the logs means that we're dividing, and so we wind up with pi over 2 times the log of 7 over 2, which is the simplification of 14 over 4 becomes 7 over 2. And if we evaluate that on a calculator, we find out that our volume is slightly less than 2, 1.97, whatever our cubic units are, cubic centimeters, cubic meters, and so forth. So where could this be used in real life? Well, this could be important in many industrial processes, such as maybe a computerized lathe creating a regular shape, as well as 3D printing, where you'd need to know the volume because of a part is where it needs to fit in a larger machine, or how much material it would take to create it. So in summary, a given function creates a 2D curve on the Cartesian plane. We rotate this 360 degrees around an axis of symmetry. This defines a 3D solid that is symmetric about that same axis. Given some starting and ending x values or domain values, we can calculate the volume of this solid. We slice the solid into consecutive circles of varying radii, where the radii are the distance from that axis of symmetry. And using the formula for area of a circle, pi r squared, in integration, we sum the area of all these circles, and gives us the result is the volume of our solid. That's it. Thanks for watching. I hope you enjoyed this. Take care. Bye.